Hi, welcome everyone. We're just going to give this a few more minutes just because we had this slight issue delaying with having to send out a new link. My apologies for that. And I'm glad to see that at least 47 of you have found the right link to connect to. Just in the meantime, so this talk is based on one that I gave for TEDx earlier in the year. And we thought it'd be a nice way to keep the activities and the exciting science and things that are going on at UK Atomic Energy Authority and around more globally in the field of fusion energy. Thought this would be a nice way to keep bringing this to you in this strange time that we all find ourselves in. So hopefully you enjoy it. And if you please bear with me for a few more minutes, we'll just give a bit of time for those who didn't receive the information on the new link to connect in. Okay, brilliant. I think we will kick off. So just before I start and going into the talk in proper, Zoom offers this interesting question and answers feature, which if you click on the Q&A box, it'll give you the ability to ask questions. I'm not going to open for verbal questions in this webinar. I think things might get somewhat difficult to organize should we do that. But what I'd like to do is offer you the opportunity to ask any questions you like on anything that I've discussed during the talk. If you write your questions down, submit them in the Q&A, then I'll spend between 20 minutes, half an hour after this webinar trying to go through the questions and submit answers. So if you have any burning questions on anything you see, anything you like, anything you don't like, please feel free to ask or contact us on any of our social media profiles, on any of our contact details. These kind of webinars are something that we're hoping to bring to you fairly regularly in this interesting hiatus period that we find ourselves in. So please stay tuned on all of our social media channels for other exciting talks from other speakers, not just myself. So to kick off, fusion energy is a very exciting field, and there's a lot of things going on. It's a very futuristic, futurology type field, and we're well on our way along the path to fusion energy. And what I'd like to do in the next 15 to 20 minutes is give you a bit of a feel for some of the exciting science that goes on in our field and what we're doing to try and bring fusion energy down to Earth. So this might seem like a bit of a strange slide to start with. I put this in here because when I was constructing this talk, I was thinking, how do I feel about climate change? I know a very cheery topic to start on, but how do I feel about climate change? And I think this chap's reaction probably sums up the reaction that a lot of us have when we talk about climate change. It's certainly true for me, and that is that we know that this is a big issue. We know that there are huge issues, huge things going wrong in the world, all to do with our impact on the climate. But it's such a big issue, and it's so intangible that very often we feel like there's not much we as individuals can do. Like this chap, his house is on fire, and he resorts to correct that by mowing the lawn. And I think that hopefully I don't just speak for myself when I say that I feel like we have similar attitudes to climate change. I know it's an issue, but I still drive a diesel car. And part of that problem is intangibility. It's such a big issue that it's very hard to consider what we need to do. So I thought I'd try and bring some numbers to this first for you. Apologies for those with any kind of allergies to numbers, but hopefully this will make some sense. This is a prediction by the International Energy Agency for what our energy needs, energy requirements will be in the year 2040. Now, this is a bit of a weird unit, this MTO unit. It's not some weird body part. MTO stands for million tons of oil equivalent. So this is the equivalent amount of oil that we will have to burn in order to get a certain amount of energy. So in 2018, we used globally, all around the world, we used 14,300,000,000 tons of oil equivalent. Of that, 11 billion tons was in fossil fuels. So fossil fuels are this purple, red, and brown that you can see here. That's a lot of energy. And what that means is that if we want to decarbonize our energy supply by 2040, this is the amount that we have to get rid of. At the moment, populations are growing, and so our energy demand is growing. The fossil fuel part that goes into our energy demand looks to be leveling out. But what we really want to do is this. We want a zero carbon energy supply for the future. And that means that we have to replace 11 billion tons of oil equivalent in order to achieve this. This is obviously a phenomenal challenge. There are lots and lots of different aspects. It's a very, very complex issue. And I'm not going to try and say that fusion is the answer to all of this. But what I want to do is kind of set the climate that fusion enters into. And fusion has a part to play in establishing this zero carbon energy economy of the future. Of course, what you would like is you would like a safe source of energy. You would like a source of energy that is abundant. You would like a source of energy that is renewable. You would like a source of energy that doesn't produce any kind of carbon. And we have that in the sun. We all know about solar power, but the power that actually powers the sun is fusion energy itself. And we've known about this since the 1920s. So Sir Arthur Stanley Eddington was a real pioneer of his time and probably the first fusion physicist. And he said of the sun, of the core of the sun, that this reservoir of energy can scarcely be other than the subatomic energy which exists abundantly in all matter. We sometimes dream that humanity will one day learn how to release it and use it for their service. This store is well nigh inexhaustible if only we could tap it. And what he's talking about here is the energy that is powering the sun. He also said, so that at the time, this was met with quite some skepticism because this was a really, really new idea that, that this kind of subatomic energy was able to power something as huge, as enormous as a star. And to that skepticism, he replied, "We do not argue with a critic that urges that stars are not hot enough for this process. We tell them to go find a hotter place." Now, it's a shame that Eddington died in the 1940s, because actually now we know that there are hotter places in the universe that exist where fusion is certain to occur. One of those is here. This is Culham in Oxfordshire. This is the UK Atomic Energy Authority lab. And in this building, when the machine is running, we have a volume of space that is 10 times hotter than the center of the sun, where we do fusion regularly. Now, fusion in the sun is based on hydrogen. So it's two hydrogen atoms collide together to form helium. But this is particularly inefficient. It's a very bad fusion reactor, and we have to do better here on Earth. So we don't use hydrogen. We use deuterium. And deuterium is one proton and one neutron. And this fuses with tritium, which is one proton and two neutrons. And these form helium, two protons, two neutrons, and a lonely neutron that flies off. And the neutron flies out of the vessel, carries with it a lot of energy, and it's the energy in this neutron that we will harness and use to create electricity. Now, deuterium and tritium, well, deuterium is very, very abundant on Earth. So about 1 in every 6,000 hydrogen atoms in water is actually deuterium. So we don't have to worry about deuterium, we can get that readily. Tritium, on the other hand, is not so abundant. So tritium is radioactive. It has a half-life of about 12.3 years, which basically means if I take a kilogram of tritium and I leave it for 12 years, I end up with only having half a kilogram of tritium at the end of it just because of radioactive decay. So we have to do something about this. Fortunately, if you instead take lithium and you bombard lithium with neutrons, then you can produce tritium as a byproduct of that reaction. So all we need actually to get fusion to work is we need deuterium and we need lithium. And it turns out that the energy density, the amount of energy you can get from fusion is so intense that if I take a bathtub of water, if I take the deuterium from a bathtub of water, and I take the lithium from 2 laptop batteries, I've got enough energy there to displace 40 tons of coal or 250 kilograms of uranium ore. So the energy density is huge. It's phenomenal. And it's for this reason that we really feel the need to harness this energy and produce it and turn it into electricity for humankind to live off. Not only is it energy abundant and high energy yield, but there is no carbon in this reaction. You don't see carbon anywhere in this reaction. So we don't produce carbon as a byproduct of this energy source, and that makes it a very desirable option. So how do we build a fusion reactor? Well, what we'd like to do is we'd like to take the sun, we'd like to put the sun in a box, and we'd like to extract all that nice juicy fusion energy from the sun and plug it into our TV. Unfortunately, the world is somewhat more complicated than this. How do we actually build a fusion reactor? We use machines called tokamaks. Well, I should say there are many different approaches to doing fusion on Earth. Probably certainly the most well-developed of these approaches is the tokamak. And tokamak stands for this is an acronym for this Russian sentence here, which I'm not going to embarrass myself and try and pronounce. But this means toroidal chamber with magnetic coils. And a tokamak is a very complicated machine, but it boils down to 3 kind of essential components. Firstly, we need something called a plasma in the middle of our machine. So if you take a gas, so any gas you want, and you superheat that gas, you heat it to millions and millions of degrees, all of the electrons that are flying around all of the atoms in that gas will be stripped away. They'll be liberated and they'll move completely freely from the atoms in that gas. So now all of a sudden you have electrons moving in one direction, you have ions moving in another direction, and that is called a plasma. So plasmas exist everywhere in nature. Something like 97% of all of the matter in the known universe is in the plasma state. So plasmas are really, really prevalent all around the universe. It just so happens that here on Earth, the conditions are not very good for plasmas. So we have to do something about that. Now, because everything in a plasma is charged, so you have electrons moving around, they have a charge. You have ions moving around, they have a charge. They can respond to magnetic fields. It's like having an iron filing or something responding to a magnet. And we can use that to our advantage. And we use that as a kind of cage. We create a magnetic cage that this plasma sits inside. So the burning hot plasma, burning at hundreds of millions of degrees, doesn't get anywhere near touching a wall or damaging a component we don't want it to damage. And this is the illustrious hand of our CEO at the UK Atomic Energy Authority. And he's showing you here that if you move a magnet around a plasma, the plasma responds because of the magnet being moved. And this is exactly the principle that we're working on here. So by creating a huge magnetic field cage that we keep our plasma in, we're able to keep it in a fixed volume of space for a sufficiently long time that we can superheat it and we can start to get fusion to occur. We also need to put this somewhere. So if we just did this in open air or in an ambient environment, it wouldn't work very well because you'd have lots of nasty things like oxygen, nitrogen, all of the things that you don't really want getting into your fusion reactor. So we confine it in a vacuum vessel. And the vacuum vessel is in this donut shape that we call a torus. And this is the kind of fundamental aspects of what make a tokamak a tokamak. Now, lots and lots go into making a tokamak run. So it takes tens to hundreds of people to get one of these things running. You have to heat it, you have to fuel it, you have to measure things, you have to keep it all under control. So they're very, very difficult things to keep running. But at its core, this is what makes a tokamak a tokamak. Now, there are something like 60 to 70 tokamaks around the world. We've known about tokamaks since the 1950s. They emerged out of Russia in the late 1950s, and the rest of the world adopted them in the 60s. They've been the leading fusion concept for nearly half a century, and we still don't have fusion power. And you'd be well within your rights to ask, well, why don't we have fusion power? Why is fusion power still unobtainable to us here on Earth? Well, actually, we're doing a bit better than we make out. So this is a bit sciencey. I apologize to anyone who I promised that we wouldn't get too sciencey, but I just couldn't resist a little science in this talk. Some of you may be aware of this thing called Moore's law. So Moore's law is something that's around, it has been around for many years, and Moore's law documents how fast your computer chip runs. So this yellow line you can see right in the middle of this graph, this is showing you that every 2 years, the speed of a computer chip doubles. So the speed of a computer chip doubles every 2 years. So that's pretty cool. And that means you can basically say in about another 2 years, if all technology remains the same, we should have twice as fast computers as we do now. Now this blue line is the same kind of measure, but it's fusion machines rather than computer chips. And this is saying how close are we to actually achieving fusion, which is up here, indicated by this green arrow. How close are we to achieving fusion? And we're actually outpacing Moore's law. We're doing better, we're getting closer than Moore's law for computer chips. So fusion devices, tokamaks, get better get twice as good about once every 1.8 years. And you can see that here in this line down in the left-hand side of the graph. So what's going on here around the late 1990s, which means that all of a sudden this stalls? Well, the next thing we've got in the blue line is this thing called ITER. And ITER is a very, very different beast to everything else that we've tried to tackle on Earth before. All of these things in the left-hand side, you could call concept-defining experiments. They are the experiments that we're running to boost performance, to get the performance of the machine as high as you possibly could, to get as close to fusion conditions as you think you can get. And they achieved that. They did very well. But the thing in the top right-hand corner is a different beast altogether. This is an energy-producing reactor. This is something where I'm going to put a certain amount of energy in and I'm going to get 10 times that energy out. And that brings with it a whole host of different issues that we didn't have to deal with before. Things like, how do I make sure that everything is safe? How do I make sure that I'm actually producing enough tritium to keep the machine running? So there are all of these issues now that we face, which are, they are scientific issues, but they're also engineering issues. They're technological issues, things that you didn't have to worry about when you're defining the concept, when you're doing the experiments that get you to this peak performance. And that's the difference now, is that we're now on the path to producing fusion energy. So whilst we are still 20 years, 30 years away from fusion energy, we're actually a lot further along the path than these kind of simple statements make clear. And this is ITER. ITER is an absolutely phenomenal project. And I really, really encourage anyone tuned in to go away and read about ITER after this talk, because it is just amazing in every respect. ITER is a global collaboration of 27 different countries, of 7 different member states, all coming together to try and make fusion a reality. So all coming together to contribute to this one experiment and make fusion a reality. Now, something like 50% of all of the world's population are represented in ITER somewhere. And around 90% of the world's economy is represented in ITER. ITER is really an undertaking the likes of which we have never seen before. And it's not just challenging from a management point of view, it's challenging technology in every respect. In everything it does, it's pushing technology right to the bounds of what we're able to do as a human race. Now, ITER will produce 10 times the power output that gets put into the machine. So that means that fusion will be proven. So if we can produce more energy out than we put in, we've proven that fusion can occur, and we can then build fusion reactors that can produce electricity. But more importantly, ITER is going to do something called achieving a plasma burn. And a plasma burn is where the heat that is produced because of the fusion going on right at the core of the machine is enough to keep that fusion reaction going. And once you can achieve that, then the sky is your limit. Well, actually, probably technology is your limit. But once you can do that, you can really start to dream of machines which are going to produce much, much more than 10 times the power out than they put in. ITER is amazing for so many different reasons. The magnets in ITER are strong enough to levitate a jumbo jet. The heating systems in ITER are strong enough that they could vaporize a car in seconds. It's about the same size as a football stadium. It really is a absolutely phenomenal project. And this video that I'm showing you now is actually outdated. I didn't have time to put it in these slides, but I encourage you to go onto the ITER website and look at the latest video that they've put up, because the level of progress that is being seen in this project now is very, very exciting. So ITER is due to come online in 2025 with fusion experiments likely to occur around the 2030s. Now, ITER is exciting, ITER is amazing, ITER is going to be the proof that fusion works, but ITER is not the solution. The reason that ITER is not the solution is because ITER will not produce all of its fuel self-sufficiently. It will not produce the kind of power, or at least the kind of economy, that we need for a fusion reactor. And there are many challenges that stand in the way of creating the fusion solution. Among those challenges, we think 6 of the biggest challenges are highlighted here. So, number 1, how do I make the hot parts of the plasma hot enough to do fusion reliably? Number 2, I've got all of these neutrons flying around. I said that the byproduct of the fusion reaction are these neutrons that fly out of the machine. They carry huge amounts of energy with them, and they can be very, very damaging to anything you put in their path. So we need to create materials that can withstand this really, really harsh environment. It's a harsher environment for materials than anything else that we know of on Earth at the moment. If we've got all this heat burning at the center of our plasma, we need to make sure that we don't overheat all of the materials in the machine. We need to make sure that we can safely remove all of the excess heat that we can no longer use for fusion. And we need to do that in a way that will keep the machine running and won't mean that we have to repair it. The machine has to be self-sufficient for fuel. So we have to be able to create enough tritium within the machine in order to keep that cycle going. So we do fusion, we create tritium, we pump that tritium back into the machine, we do more fusion. And that has to be self-sufficient. So that cycle has to be continuous. And if we can do all of that, if we can make everything work, then we're going to want to run these machines for years, months or years at a time. By the end of an operational campaign of one of these machines, they are not somewhere that you will want to walk in. You will not want to take a stroll in the tokamak. So if you want to do any maintenance on the machines, if you want to do any kind of repairs or strip away or replace any components, you're going to have to do that all robotically, all remotely. You don't want a human in that environment. And finally, if you can do all of this, you have to do all of this in a single engineering design that fits together like a jigsaw. And this is not a trivial point. Now, I don't want to go through all of these because there's so much you could say on any one of these topics, but I'll take 3 of them and just quickly cycle through some of the very exciting science that's ongoing right now to address these issues. We're not just looking at ITER, we're looking well past ITER, right into the future, and we're addressing the challenges that will allow us to create the fusion solution. So how do we create a burning plasma? The hottest plasma in the world at the moment is in JET. JET is the Joint European Torus. It's housed down at Culham in Oxfordshire in our lab at the UK Atomic Energy Authority. And JET is a machine run by UKAEA on behalf of Eurofusion and the European Commission. This is the inside of JET. It's all nice and shiny and metallic. And actually, JET looks like a scaled down version of how we expect ITER to look when it comes online in 2025. And I can show you what JET looks like when it's running. So JET holds the fusion record. JET has produced 65% of the power back out that we put into the plasma. And this is quite phenomenal. So 65% of all the power that went in got produced back out as fusion neutrons. And this is what JET looks like when it's doing a fusion experiment. Now, what I really, really like about this video is if you look carefully, you can see lots of speckles on the camera. I'll just rewind it. So you can see lots of speckles on the camera all around here. And they look a little bit like my camera's going wrong. They look like dead pixels, but they're not. They are fusion-born neutrons coming out of the plasma, hitting the sensor of the camera, and killing that sensor for a small portion of time. This is really cool because this means effectively we can see fusion. We can see fusion going on. Now, there are lots of other ways we can measure it as well, of course. We can measure the neutrons that come out of the plasma. We can see how hot the plasma got in the core. But we can do fusion in JET. So fusion happens regularly in JET. And it's a very exciting time in JET at the moment because it's about to go into a new fusion campaign. So we expect next year JET to go into a new fusion campaign. The goal will not be to beat the record, but the goal will be to take that record of energy produced, and rather than produce that amount of energy for half a second or a blip in time, we want to do that in a nice controlled fashion to show that we can operate this machine at the high performance that we need for a fusion reactor in a controlled way. And once we can do that, we can be reasonably assured that we will have the absolute best start we can hope for with running ITER. So we've got the hot bits hot. We've got the center of the machine as hot as we think we need it for fusion, and we can do fusion reliably. But how do we keep the cold bits cold? We have a second machine at the UKAEA in Culham, and this is called Mast Upgrade. And this is a beautiful machine. This is a rendering of it here. Now you'll notice that Mast Upgrade is a bit smaller. It looks a bit different to Jet. What we've done with Mast Upgrade is we've pushed everything much closer to the center. Now this is great because it means we can operate the machine more cheaply. It means it doesn't need to take up so much space, but it's not so good if you want to handle heat. Because if you imagine that you have some, I don't know, a hose gushing water out, your heat is now your water, and it's gushing, and the end of the hose is really, really big, then the amount of water that actually comes out is reasonably sparse. It's quite dispersed. It's not going to give you a huge flow of water hitting anything, hitting the ground. But if I now make that entrance much, much smaller, and I'm still pumping the same amount of water through that hose, the speed at which that water is going to come out is going to drastically increase. And that's essentially what happens in here in the tokamak when you make it smaller. And that means that the amount of heat that goes down and hits these surfaces will go up rapidly. And we need to be able to deal with that. And that's exactly what these chambers at the top and the bottom of the machine that you can see are designed for. So this is something really exciting called the Super X diverter. It's a bit of a fancy name, but what it essentially is trying to do is it's trying to take the bit of the plasma that is very, very hot. And here on the left, the bit of the plasma that's very, very hot is this bit that's red on the left. And it's trying to isolate that part of the plasma from the bit of the plasma that we want to keep very, very cold. And that's the bit down in this graph on the left, that's the bit in the bottom right-hand corner. And we think this solution will allow us to keep the cold bits cold and keep the hot bits hot, and to do so in a nice, controlled, sustained manner. And if we can do that, if we can prove that that is possible, then we can start to look at scaling up this solution for future tokamaks, future power plants in the future. So this is really exciting, and this we expect to come online. Well, I should say I wrote these slides before March this year, so treat this with a word of caution, but we expect this to come online very soon. And it's a really, really exciting world-leading machine. And finally, like I was saying, if we can get everything going, if we can keep the hot bits hot and we can keep the cold bits cold, and we can run the machine, eventually we're going to have to stop it, and eventually we're going to have to do some repairs. Now, what kind of repairs might you want to do? Well, you might want to go in and repair a pipe, for example. You might want to re-weld a pipe. Something that sounds kind of trivial, right? You can just go in and re-weld a pipe and leave. But it's not so trivial when you have to do it with robots, and you have to design special solutions like the one that's playing in this video here, where you have a trio of robots that are all working in tandem to inject this snake-like robot along the pipe. Once the robot in the pipe gets to its site, gets the bit you want to re-weld, a laser cutter spins around and cuts through the bit of pipe that you're going to replace or re-weld. Once it does so in a kind of controlled manner, and it collects all of the waste that it produces, all of the weld waste that it produces. And this allows you to do a remote cut. So it allows you to cut the pipe, extract the pipe, and replace the pipe with a new module if you need to. All done by humans, which are operating these things from many, many meters away, many hundreds of meters away in some remote control room. Now, all of this looks like science fiction, right? It looks like the kind of thing that people play around with on computers and come up with fancy things on computers. But actually, these exist in real life. So this is a prototype of this robot. And these pipe bits that you can see here, these are two lengths of pipe that were cut in half by this welding robot. So all of these solutions need thought. All of these simple jobs that are simple when the human can come in and do it are very, very hard when you need to do it with robots. But these solutions are all things that are being worked on right now to try and address all of the gaps in our technology, all of the gaps in our knowledge that stand in the way from making fusion a reality. But you don't need to take my word for it. So obviously I think fusion is awesome. And hopefully several of you now think fusion is even more awesome than you already thought it was. But you don't need to take my word for it. So before he passed away, Stephen Hawking was asked in one of his final interviews, what world-changing idea, small or big, would you like to see implemented by humanity? This is easy, he said, and I should say this is not easy, but he said this is easy. I would like to see the development of fusion power to give a clean, unlimited supply of energy. And this is what we're working towards. And we're well on the pathway to delivering fusion energy. Now we have machines like JET, which are providing us the solutions, providing us the training, providing us all of the data that we need to start to look at bigger machines that are going to prove the concept, like ITER. ITER will come online. ITER will produce more energy out than it put in. ITER will be the proof that fusion is a reality. Alongside all of this, we're addressing all of the challenges, all of the pitfalls that stand in the way of making fusion a commercial success. And once we've done that, we expect to be building things like this on the right-hand side. Fusion power plants that are powering the generations of the future for hundreds, thousands of years to come. Thank you very much. That is the end of my talk. So I really appreciate you all tuning in. And I will go through the Q&A session. If anyone has any questions they'd like to ask, please drop them in the Q&A chat, and I'll do my very best to get to all of the questions that have been asked. Thank you very much for tuning in. I hope that was interesting. I hope that was useful. And please keep an eye out on all of UKAEA's social media, because we expect to have a lot of things that we can bring to you in the next few weeks. A lot of exciting talks from people much more interesting than me. So please keep an eye out and send any questions into the chat or to any of our social media accounts or to me personally. Thank you very much. I appreciate your time.